BC 10.5. Okay, this is a short 2 problem for response worksheet. Kind of give you some extra practice with for response. First problem is graphing calculator. Particles move along a curve that says position at time t, xt, yt is given. So this is parametrics, two-dimensional motions. They're giving you the position for x and y. Well, actually, y is not given to you, but x and y are measured in meters, seconds, so probably won't put units. It's known they're giving the derivative of y, so that's interesting. So part A says to find the speed of the particle at t equals 3 seconds. So remember, the idea here is that we have a velocity vector that we can break down into Vx and Vy components, their own separate vectors. The speed is the absolute value of velocity. It's the magnitude of this vector. It doesn't care about the direction. And so this is just Pythagorean theorem idea. So speed at time 3 equals the square root of x prime or dx dt squared plus dy dt squared at those times. Now you have a calculator, so I mean you might take advantage of that. The derivative. Now I'm going to put this equation in here. X, I don't know, whatever. I guess it'd be easy enough to find dx dt on our own. Let's just do it. 2t minus 4, right? So we're going to plug 3 into this. It's going to be 2 squared plus, we're going to plug 3 into that. It's going to be 3 times e to the 0, which is so when you plug 3 into this, you're going to get e to the 0, which is 1 times 3 is 3 minus 1 is. So that's going to be 2 squared. So it's going to be the square root of 4 plus 4, which is the square root of 8, which is 2 root 2, or square root of 8, or but I feel like I made yeah. So there we go. So it is, and it's the units are meters per second, or you could have used a calculator, and you get 2.828 meters per second. So there you go. That problem was worth 1 point because it's pretty simple and straightforward. B, find total distance. Now, distance is the integral of speed, just like it was with one-dimensional motion. And so it's the integral of dx dt squared plus dy dt squared dt. And so for us, distance is going to equal, now it says from time 0 to time 4, integral of dx dt is 2t minus 4 squared plus dy dt was t minus 3 minus 1 squared dt. Show the setup, put the dt, put the limits. This is worth a point, 1 point for doing that. Then we can do our calculator. Don't plug in time 4 in any of this stuff right now. So let's see. I'm just going to type this in. Math 9. Square root parentheses 2x minus 4 squared plus parentheses x e to the x minus 3 close minus 1 close squared close comma x comma 0 comma 4. So that's what we should have. Let's see what it gives us. Just patiently waiting. Take a deep breath. 11.587 or 11.588 meters. All right, distance. So 1 point for the setup, 1 point for the answer. C says find the time 0 to 4 when the line tangent to the path of the particle is horizontal. Is the direction of the motion of the particle towards the left or towards the right at that time? Give a reason for your answer. So this is two-dimensional motion. It could be horizontally going to the left, or it could be horizontally going to the right or left. So first of all, the path is horizontal tangent when just like with any curve since last year in Calc AB, we want to know when is dy dx equal to 0. Now, by the way, just writing that down is worth a point. You should be writing that down anyways. Like, okay, that's what I'm trying to do. Now, dy dx equals dy dt over dx dt for parametrics. And so we have dy dt is t e to the t minus 3 minus 1 over dx dt. We figured out earlier was 2t minus 4. And we want this to equal 0, which means the top has to equal 0, right? So that means that dy dt t e to the t minus 3 minus 1 has to equal 0. But I guess we got to also make sure that dx dt doesn't equal 0 at the same time, because otherwise that's a indeterminate form and we'd have to do more work to figure it out. Now I'm going to use my calculator to solve this, because that looks like that would be potentially hard to solve without a calculator. So I'm going to put this in here, x e to the x minus 3, close parentheses, minus 1, window. We're looking specifically from 0 to 4, and we're looking for the x-intercept of this graph. So I'm going to do negative 1 to 1. I don't need to see the whole graph. And it could be more than one answer, but there's one. So second calc 0, looks like it's around like 2.2. So I'm going to say 2 to 2.5, guess 2.2, 2.20794. Okay. So the first answer is, that it is 2.207 or 2.208, and the units are seconds. Okay, so that's that. And then it says, is it going towards the left or the right? Well, that's where dx dt comes in. So we're going to end up checking dx dt anyway. So we're going to plug time equal 2.20794. I'm going to carry extra decimals right now in the middle of my work when I calculate something else. And we're going to plug it into, I guess dx dt is this. And then we could figure out what that answer is. 2 times 2.20794 minus 4 equals 0.41588. And since that's positive, that means it's moving to the right, because x is in the left right direction. So we're going to say since dx dt at time 2.207 equals 0.415 is positive, the particle is moving toward the right at time t equals 2.207 seconds. So this would be meters per second, by the way, units for that, if we just wanted to be extra careful. Point-wise, you got a point for just setting dy dx equals 0, because that's like, hey, that's a big deal. That means you understand what a horizontal tangent is. And then you got a point for getting the time, and then you got a point for deciding if it's moving left or right in the work that would support your answer. D says there's a point with the x-coordinate 5 which the particle passes twice. So it says that it goes through x equals 5 twice. Find each of the following: the two values of t when that occurs, the slopes of the lines tangent to the particle's path at that point, and the y-coordinate of that point, given that y2 equals 3 plus 1 over e. So the first thing to do is to figure out, well, where does it equal 5? And so if you want to figure out when x equals 5, you set the equation for x equal to 5. Now we could see if we could solve this. Let's see, equals 0. T, I mean, I can use my calculator to solve these, but if it's simple enough, minus 3 minus 1. Oh yeah, this is easy. So t equals 1 and 3 seconds. Okay, so that's the first part. That's worth a point, and you need that for the other parts. So then the next part says, so this is I, and then the second part is what the slopes of the lines tangent to the particle's path. So that's dy dx. So we're looking for dy dx at time equals 1, which means we're looking for dy dt over dx dt at time 1. And so I think we already used this earlier, this idea. So dy dt, I mean, we can use a calculator, but we could just plug it in 1 times e to the 1 minus 3 minus 1 over 2 times 1 minus 4. So that's going to be e to the negative 2 minus 2 over negative 2, which we could write as, I mean, we could probably just leave it like that if you want. It's ugly, but it's fine for response. But as a decimal, it would be 0.932. So that's the slope at time 1. And then dy dx at time 3 equals dy dt at time 3 over dx dt at time 3. And I mean, we could just write it in. It'd be a 3e to the 3 minus 3 minus 1 over 2 times 3 minus 4. That would give you e to the 0, which is 1. So I give you 2 over 2 is 1. Okay? All right, kind of running out of room here. The third thing says to find the y-coordinates at each of these points. Given that, so they give you that y2 equals 3 plus 1 over e. Now, you have two options here. Not that you legitimately have two options, but they didn't give you y earlier. They gave you dy dt, right? So we could say, oh, well, we could integrate that. Let's find the y equation by integrating dy dt and doing plus c and use the initial condition. So you'd use this initial condition to find the plus c. But here's the deal. You can't integrate this. So you got to rely on your calculator. Plus, even if you could, you want to rely on your calculator for this. This is perfect setup for fundamental theorem of calculus part 1. Okay? FTC part 1 says, okay, well, if we integrate y prime from some known value to some other value, so I usually go with the smaller, I want time 1, I was given time 2. That's going to give me y2 minus y1. So then that means that y1 equals y2 minus 1 to 2 of y prime dt. And so I'm going to put that in my calculator. Now y2 is 3 plus 1 over e. And then for the other one, we're going to do the same kind of thing. We're going to say, okay, well, we know time 2. Let's go to time 3, which we want, of y prime t dt, and that's going to give you y3 minus y2, and we want y3. So on this one, we're going to do y3 equals y2 plus the integral of 2 to 3 y prime dt. and then y2 is 3 plus 1 over e. So we can put those in our calculator. I think did already put so I already have y prime in my calculator, so I can do vars y vars. So I'm going to do 3 plus 1 divided by e minus math 9 vars y vars function y1 comma x comma 1 comma 2. So this is the first one. The y value is 4. Okay. And then the next one, second, it's going to be plus, and it's going to be 2 to 3. So that one is going to equal 4 also. So that's kind of interesting. So that was a point. So that whole that was our 3 points, 1 point for each part. But recognize the need for fundamental theorem of calculus part 1, or just the opportunity to take advantage of it on your calculator especially. Okay? All right. Okay, so next one is an opportunity to practice logistic and Euler's method and even some series all in one. It looks like a good one. Differential equations, slope fields. So that's a differential equation, logistic differential equation. Does it look like what you remember? Logistic, which you're probably going to need this, is ky has the exponential part and then m minus y. Right? That's carrying capacity, and that's your growth rate. Let y equals ft be the particular solution to the differential equation f(0, 8). Particular means one specific one. This is your initial condition. A slope field for this differential equation is given below. Sketch possible solution curves through points 3, 2. So 3, 2 is right here. They even put a little dot here. So we're going to follow this along the slope field. We shouldn't cross any of these, and we should put arrows on the ends. And it should look like it's going towards those horizontal asymptotes. Now that's the logistic curve we usually think of probably, but there are other solutions below this and above this band that have different shapes. 0, 8, for instance, is up here, and it goes like this. It goes towards that horizontal asymptote, but it doesn't have another horizontal asymptote above it. So that's that one. So that's worth, I don't know, at least, let's see, 2, 4, 5, 1, 2, 3, 4, 5, 6, maybe 3 points, probably 2 points. I'm assuming 2 points. Okay. Now, so that's not really a BC thing so much. They gave you slope field is done, so sketch the particular solution curve on the slope field. B says to use Euler's method starting at t0 with 2 steps of equal size to approximate f1. So this is typically, if they're going to have you do Euler's, they're not going to make you do like 5 steps. So the whole table thing isn't as beneficial. And the table thing I think is potentially dangerous because you just might not remember how it works and you won't get any points. I think they should be okay with the table as long as you kind of have things labeled right. But for response, I would try and do it the normal way. We're just doing tangent lines twice instead of once. So we know we're trying to find f1, and we have f0, and we're going to do 2 steps that are equal. So the steps got to be the distance from the first point to the last point divided by 2. So the step sizes are 0.5 or 1/2. And so we're going to make one tangent line at the first point. So it's going to be, this is your x, this is your y. So we're going to do y minus 8 equals. Now we need the slope. So that's where the dy dt comes in. We want the slope at 0, 8. And so that's going to be 8 over 8, 6 minus 8 is negative 2. So that's your slope, negative 2, x minus 0. So there's your first, yeah, so that's your first tangent line. Now we could put the x in for the spot we're going to use this for. It's going to be at 0.5. So, I mean, we could either change the slope-intercept form first or not and say, okay, let's put 0.5 in there. And so then y equals, that's going to be negative 1, positive 7. And this is your approximation for f of 0.5. Okay, so that's your first step. Your next step is we're going to make another tangent line. And we're going to use this point as our xy. So we got to find, we're going to do y minus 7 equals, and we got to find the slope. So it's going to be dy dt at 0.5 comma 7. And so that's going to be 7 over 8, 6 minus 7 is going to equal negative 7/8. So negative 7/8. And it's going to be x minus the previous x coordinate that we're using to write this line. So there's your equation of your tangent line. And then we're going to plug in 1 in for the x, right? And that's going to give you a 0.5, which you might realize up here, you got a 0.5. That's your delta x, right? If you're thinking of it like as far as the table, it's always the same step size. So y equals, this is going to be negative 7/16 plus 7 is going to be positive. So we could do negative 7/16 plus 7 equals 6 and 9/16. Or you could write that as 105 over 16. That's up to you. And this is your approximation for f at 1. So that's your answer. So 1 point for showing the Euler's method and 1 point for getting the answer. Now the table, which, like I said, I wouldn't write on the table. I mean, this is just makes a lot of sense. You write a tangent line, use it, get a point. Use that point to write another tangent line, use it to get a point, you're done. It's 2 steps. Who cares? If it were like 5 or 6 steps, then this would get really overwhelming and the table would make more sense. So, I mean, I'm really kind of recommending you don't do the table. If you can do the table, then you got to think, okay, well, the slope of the tangent line, you shouldn't memorize it. It's not going to work out well for you if you memorize it, guaranteed. And you might not label it well enough to get the points for it. So the point is to get points. So this is your new y, your new x, your old y, your old x, old y. This is your slope. So then y new equals y old plus y prime at the old spot. And y new minus y old is always going to be the same, so that's your delta x. So then a table would have x and y coordinates. It'd have y prime. It'd have delta x. We put in the first known point, 0, 8. We would have to, then the next point would be 0.5, and the next one would be 1. The delta x would be 0.5, 0.5. Don't need delta x for the last one. Don't need y prime either. You got to find y prime like we did, which we got negative 2. So the new y is the old y plus y prime times delta x. I mean, that's what we just did over here. So 8 minus 1 is 7. And then you repeat the process. You calculate this, you get negative 7/8. And then the new y is going to be this plus this times this. And you're going to get 6 and 9/16 or 105 over 16. I personally wouldn't do that. I think you mess it up. I don't think you really save much time. I think it's dangerous, and I don't think there's much of a benefit for it. So I don't know. This is more solid, obvious work. And for your response, you want to be very technical. This is some little trick we came up with to streamline the work. Doesn't even make sense as much here because there's not much work to streamline. C says write the second degree Taylor polynomial for f about 0. So that's the center. So it's a Maclaurin series. Use it to approximate f1. So the whole thing about Taylor polynomials was to come up with a polynomial with, x's to powers to represent any kind of other function. So we want second degree polynomial. We want to go up to the second power. We need the 0th derivative, which they gave us. F of 0 is 8, about the center. We need f prime at 0. Now this is x coordinate equals 0 or t equals 0. And so we got to use that equation, dy dt, that's your derivative, y over 8, 6 minus y. And since the y value at time 0 is 8, then you plug 8 in here. We already calculated this earlier, I think. Yeah. So there's that. And then we need the second derivative at time 0. Now, we don't have the second derivative, so we got to find the second derivative. So they gave us dy dt equals y over 8, 6 minus y. Remember, a Taylor polynomial, we need all the values of the multiple derivatives at the center times x minus the center to that power over that number factorial. And we just go from 0, 1, 2, and we're going to stop at 2 because it's a second degree, like second order. Now, the second derivative, we're going to have to say we're taking it implicitly. It might be easier to go ahead and distribute this. So I don't really want to do product rule if I don't have to, and this will make it a lot easier, I think. Or you could do product rule. So I'm gonna go with that, and then I'm gonna take a derivative of this. It's gonna be 3/4 dy dt minus 1/4 y dy dt. So if we're gonna plug times 0 in there, the y value is still 8, so it's going to be 3/4. Now dy dt is at time 0, which we just calculated. That's -2 minus 1/4. The y value is 8, and then dy dt again is -2. So that's going to be -3/2 plus 4. So that's 2.5 or 5/2. I don't think we want mixed fractions in our answer. So I think we have all the values that we need. You got a point for doing all the second derivative stuff because the first value was given to you. The second one we already calculated earlier, so that wasn't a big deal. So you got a point here. So polynomial of second order, we're going to take the first term times t minus 0 to the 0th power over 0 factorial, and then minus 2 t minus 0 to the first power over 1 factorial, plus 5/2 t minus 0 to the second power over 2 factorial. So that's just the way we build these up. Now that's going to be a 1, so I'm going to clean this up a little bit. This is going to be 8 minus 2t plus 5/4 t squared. Okay, so that's a point for getting the Taylor polynomial. Now don't forget, we have to use it to approximate. So f of 1 is the exact value. It's approximated by plugging 1 into our Taylor polynomial. And so we get a 6 plus 5/4, so that's 7 1/4 or 29/4 is the approximation for f of 1 from the Taylor polynomial. So that's worth a point. And D, what is the range of f for times greater than 0? So range of f for times greater than 0. Now, and we're not talking about y, range for y, because there's multiple ranges for y depending on where you start. F is the particular function, the particular solution at 0, 8. So that's the one up here. Be careful. That's the one up here. That's the one we've actually been using. We've been using this top one for all this work. What's the range of this? That's the y values. Now, you might be tempted to say y is greater than 6, but it said for time greater than or equal to 0. So you have to stop right here. So the range is just the y values for this. So the range of f for t greater than or equal to 0 is 6 to 8. Now it can equal 8 because it can equal 0. It cannot equal 6 because that's a horizontal asymptote. That's a point. So that was a good first response problem. Had some Eulers in there, had some logistic. It didn't really ask us about logistic so much. I mean, it was a logistic, but we were using part of the logistic solution that we usually don't. It didn't ask anything about carrying capacity or growth rate or steepest, so it really wasn't much of a logistic question. But anyways, the Eulers was good and everything else was good too.